Okay, so now we want to talk more about these magnetic forces on wires. Okay, so here are the two equations. This gives you the magnitude. This gives you the direction. So here we go. So this is an external B field. We don't know what causes it. We don't care. All we know is there's an external B field, and it circles, so it's pointing out at us. Here's a wire. There's no current. In other words, there's no moving charge. All right? So will this magnetic field produce any force on this wire if the current is zero? In other words, if the particles are not moving. What's the answer? No, right? Because you're only going to have a force if something is moving. If the velocity is moving, this is zero. Okay? All right. So if the current is zero, no force, the wire just sits there, happy as a lark. All right. Now let's say we have a current going up. Okay? So again, the B field is coming out at us, right? B field is coming out at us, and we have a wire with a current going up. What's going to be the direction? Well, first of all, is there going to be a magnetic force? And if so, what's going to be the direction? Well, just use this, right? Okay, so the current means positive charge carrier is moving up, so QV is up, right? QV is up, and I said the magnetic field is out, so QV is up, magnetic field is out, so the force is to the right. Okay? So what's going to really happen when you do this? That's what's going to happen. Okay? I mean, the wire is connected here and up there, but there's going to be a force on that wire. It's going to push it to the right. All right? What do you know? Okay? Now, let's do the other one. Let's say that the current is going down. Well, I mean, you can pretty much figure it out, right? If the current's going up and it pushes to the right, if it goes down, it pushes to the left. But let's just do it. It doesn't hurt. So QV is now down. So QV is down. B field is out, right? Palm out. You can wave if you want. The force is to the left. So the wire would actually move to the left. All right? Okay. Now, we got to get an equation, right? So here's the equation. So this is the magnetic field, this is the magnetic force on a wire caused by an external B field. So this is the current in the wire. This is the length of the wire. This is the external B field. And this is the sign of alpha, where alpha, guess what? It's the angle between the IL and the B. So that's why it's a good idea to write them. Those parentheses. I mean, mathematically, they're not necessary, but it's a good idea to write them like that because it reduces confusion. Okay, let's do a little demonstration. I'll show you this. All right, so here we have, this is a magnet. Oops, stop. Okay. Okay, so this is a magnet, and this is a piece of wire. It's not magnetic material. You can see that because it's not moving, right? Okay, so right now there's no current in it, and there's no force on it. So what I'm going to do next, I'm going to turn on the power supply. So there's going to be a little current through the wire. And it's not a huge effect. I mean, you'll see it. But the point is, you're going to see the wire move. So you ready? Here we go. See that? Okay, so there it is. All right, let me do it again. Okay, there it is, and whoop. All right. So it looks like it's magic, right? Nothing's touching it, you know? All right, so that's just this ILB sign. Okay. This is the magnitude. Well, what do you suppose the direction is? Just like we had before, you know. So that's the magnitude. The direction is this. All right, so IL cross B. Okay, same kind of thing as we had before. So if you understood the previous force law, this is nothing new. So again, you stick your right arm in the direction of IL, put your palm towards B, and thumb is the force. Okay? So you should be good at that. So again, the force is always perpendicular to the direction of the current. The force is always perpendicular to the direction of the B field. The B field and the current form a plane. Force is perpendicular to the plane. That's all there is to it. Okay? I is the direction of the positive charge carriers. L is the length of the wire. Okay, so there's two things just like before, right? There's the magnitude and the direction. And you have to know both. Maybe even the direction is more important. I mean, it's going to be next chapter, I promise you that. Okay. All right, now here's a fun one for you. So this is a circular current loop, right? So this is a circle. So we have this magnetic field going to the right. Then we have a circle. And the circle is a continuous wire, and it has a current in it. And again, so that means that the current is going in here and out here. So current's going like this, right? But this is the important part, right? Here it's out, here it's in. Okay? So you know what to do. So just use this equation. All right, use that equation, right-hand rule, and figure out what's going to happen to this circular piece of wire with a current in it. So pause your video and figure it out. Okay, the answer is, all right, why? Okay, so here, the current's coming out, right? So the IL is this way, the B is that way, right? So the force is up. Okay, here, the current is in, right? Current is in, so the IL is this way. The B field is to the right, so the thumb is down. So if you have a force up and a force down, what's this poor thing going to do? It's going to rotate. Make sure you understand this, because we're going to talk about this later when we talk about electric motors. All right, make sure you understand that. Okay. Okay, let's keep going on this. My gosh, we're going to beat this to death. All right. Now look, when we did this in a minute ago, you know, I just said this was an external B field. And then I said, I don't care what caused it. I don't care at all. It's just an external B field. And we just, okay, fine, we're happy. You know, we didn't care. Well, now we're going to change that a little bit. Now we're going to produce our own B field with a wire. Okay, here you go. So here we have a wire. The wire there's a current in the wire. And here we have this plus Q moving that way. Okay? So, here is the question. Will this charge feel any kind of force with this kind of setup? What do you think? Well, yeah, because what does a current in a wire produce? It produces a B field, right? So, I mean, here, pretend this is the wire. The current is going up. Current is going up. Grab your right hand, you know, current's going up. So the B field is like this, right? Okay, so think about it. just make these big circles around this thing. What's going to be the direction of the B field right there, caused from this wire? Well, again, just make big circles, big circles, big circles. B field's going to go in, right? So the B field from this thing, big circles, it's going to be going in here. So you have QV up, B in, forces to the left. Make sure you understand that. All right? So, forces to the left. All right? Okay, now, that was fine. Now let's replace this with a wire with a current. Okay? So now you got to be careful. Keep your eyes straight. We have an I1 and an I2, all right? So, this guy produces a magnetic field, right? Bigger and bigger and bigger and bigger. And so it's going in right here, agree? So the magnetic field from I1 is going in right there, all right? Now, so therefore, is this guy going to feel a force? Well, of course it is. Right? We just learned that equation. FB equals IL B sine alpha, right? Or the direction FB equals IL cross B. All right? Look, we have a magnetic field. This guy produces a magnetic field. This direction, right? This guy has a current, and what's the sign? Okay, what's the angle? So the B field is this way. The B field from this wire is this way. This is this way. What's the angle between this and this? 90. What's the sign of 90? 1. All right, isn't that nice? Okay. All right, so IL cross B to the left. Okay. So the force that this guy exerts on this guy is to the left. All right? So what is that? Okay, now let's go the other way. I2 is producing a magnetic field, right? So grab that wire, and it goes like this, right? Bigger, bigger, bigger. So what's the direction of the B field right there? It's coming out. Agree? It's coming out, right? Grab that wire, coming out. Okay, so IL cross B that way. All right, so what does that say? It says if you have parallel wires with currents in the same direction, what do these wires do? They attract, right? They attract. Okay? So we say that parallel currents attract. It's easiest that way, right? Parallel currents attract. So what do you think is going to happen with anti-parallel currents? If parallel currents attract, what are anti-parallel currents going to do? Repel. And you can figure that out on your own. Okay. So there you go. So all right, so remember, parallel currents attract, anti-parallel currents repel. All right, so here's a question. See if you know what I'm talking about. This is an awesome question. I wish I could do the demonstration, but it'd probably be illegal because it requires mercury, which is hazardous to the max. The drawing shows a conducting wire. Well, most wires are conducting, right? Anyway, the wire shows a conducting wire wound in a helical shape. So it's like a spring, right? The helix acts like a spring and expands back towards its original shape after its coils are squeezed together and released. Okay, fine, it's a regular spring. The bottom end of the wire just barely touches the mercury, and mercury is a super awesome conductor in the cup, right? Right? So this thing is touching the mercury. Okay, after the switch is closed, current in the circuit causes the light bulb to glow. So does the bulb glow continually, grow briefly and then go out, or repeatedly turn off and on? So please, everybody, don't just humor me. pause your video and do not turn it on until you have this thing figured out. It's not easy. But if you've been paying attention for the last 5 minutes, you'll figure it out. But you probably have to read it again. Okay, let's talk about it. So look, right now it is an open circuit because the switch is not closed. So the light bulb is not going to glow, right? When we close the switch, we have an open circuit. A closed circuit. Close the switch, we have a closed circuit. So this is the conductor. So we have current going all the way around, and the light bulb will glow. However, what's going to happen though? As soon as we have a current going through this spring, we have parallel wires, right? And what do parallel currents, right? And what do parallel currents do? They attract. Well, so what's going to happen to the spring? It's going to compress, right? Which means it's going to not touch the mercury anymore, right? And if it doesn't touch the mercury anymore, we have an open circuit, so the light bulb is going to go out because it's not a complete circuit. Now, what does that mean? When this thing is no longer touching the mercury, the current is going to drop to 0. So that means that the spring that was compressed will now stretch again, right? And then it will form a closed circuit. Light bulb is going to light or glow, but then this is going to compress again, and so forth and so on, right? So we're just going to keep going off and on, off and on, off and on. Make sure you understand that. It's a good question. All right, now we get to the tough part. Now we can talk about forces and torques on current loops. So here are the directions, crucially important. A rectangular loop is placed in a uniform magnetic field with the plane of the loop perpendicular to the direction of the B field. So what they're saying, just pretend this is a rectangle. So they're saying that you have a rectangular loop of wire, and the B field is this way, right? So here's the plane of the wire, and this is the B field. So the B field is perpendicular to the plane of the wire. Okay. A rectangular loop is placed in a uniform B field, plane of the loop perpendicular to the direction of the B field. If a current is made to flow through the loop in the sense shown by the arrows, so for me that would be counterclockwise, what does the magnetic field exert on the loop? So you want to use these equations, especially this one. Well, both of them, but all right? So pause your video, figure it out. This is important. Okay, let's do it. So here, the current is this way, the B field is that way. So what's alpha? Alpha would be 90, sine of 90, what did I just say? Oh, yeah. So sine of 90 is 1, right? Okay, so here, hold on just a second. IL cross B, yeah. Okay, so IL cross B, the force is going to be this way, right? So the force is going to be that way. Okay, here, IL is into the board. B field is up. Of course, it's going to be that way, right? So again, pretend this is a rectangle. Force that way, force that way. Okay, here, IL is this way. B field is that way. Force is that way. Here, IL is this way. B field is that way. Force is that way. Okay, so what am I saying? Force that way, that way, that way, that way. What's going to happen? Nothing, right? Everything's going to cancel, right? The forces are all going to cancel, and nothing happens. And it's not going to rotate, right? Because all the forces are in the same plane. Okay, so that was the easy one, right? That was the easy one. Nothing goes on. There's not a net force. There's not a net torque. The forces cancel. There's no rotation. Okay, now is the crucial one. A rectangular loop is placed in a uniform B field with the plane of the loop parallel. Okay? So here, I should have used this before, huh? So here's your rectangular loop. Pretend, you know, your wire loop. And now the B field is like this, right? So the plane of the loop is the plane of the same direction as the B field. If a current is made to flow through the loop in the sense shown in the arrows, what does the magnetic field exert on the loop? Okay, so crucial question. So pause your video and figure it out. Okay, let's do it. So here, IL is this way, B field is that way, force that way. All right, so on this lower piece of wire, or this lower segment of wire, force is out. Okay, here, the IL and the B are in the same direction, so that means that alpha is 0, sine of 0 is 0. So there's no force on this segment of the wire. Okay, let's do this one. So IL is this way, right? IL is this way. B field is that way, so the force is in. So remember, this is out here, nothing here, in here. Okay, this way, the angle is 180, sine of 180 is 0, so nothing. So what you get then, like I said, you have a force this way on this bottom piece, this way on this top piece. So what's it going to do? What's this thing going to do? If there's a force here going like that, force going like that, what's this thing going to do? It's going to, right? It's going to rotate. Okay? Now notice the forces are going to cancel, right? Because, you know, this is equal and opposite to that, so the forces are going to cancel. But the fact is that they're at different locations, you know, so it's going to make the thing spin. Okay? So force that way, force that way. So it's going to spin. So we're going to get a net torque, a net torque. Oh boy, well, you know, we learned this in Physics 105, so let's calculate the net torque, all right? Now notice, again, there's really two torques, right? 1, 2. So we're going to multiply it by 2. And this has nothing to do with it, right? Because the force here is 0, force here is 0, so we just care about this and that, okay? All right, so... Okay, so that's the equation for the force, and we already discussed the fact that alpha is 90, sine of 90 is 1. So we just have this, right? So just ILB, okay? All right, now, who remembers what torque is? So torque is the force times the lever arm. All right, force times lever arm. And the lever arm is perpendicular distance from the force line to the axis of rotation. Okay? So hold on, don't worry, we'll explain it. Okay, now this is, all right. So this is one view. Now pretend I'm over here. Okay, so pretend I'm looking at it like this. Okay? So we're going to look at this from the side view. And we're going to pretend that this thing is like, you know, not like that, but like this or like this, okay? All right? So sort of makes sense? So this is the side view, you know, all right? So I don't know, okay? So I hope that makes sense, okay? So there's the current loop, right? Here the B field is coming out, and, okay. All right, so what we want to do again is we want to calculate the torque. All right, so let's do it. Okay, first of all, like I said, there's two torques, right? Because there's the force, you know, here and here. So there's 2, and the force is ILB. Okay, now lever arm, that's what drives everybody crazy in Physics 105, right? The lever arm. Okay, so let's do it. So this is the force line. We're just going to do it from 1. So here's the force line, right? Here's the force line. And the lever arm is the perpendicular distance from the force line to the axis of rotation. Well, there's the axis of rotation. So where's the force line? So that's the force line, right? Oh yeah, so we're going to have a square current loop to make it simple, right? The square current loop has dimensions L by L. Okay, so this is the lever arm, right? So what is that lever arm? Well, we know this angle. Okay, we know this angle. Okay, this is L, so this is L over 2. This is opposite, right? So it's just going to be L over 2 sine theta. So it's going to be, so the lever arm is L over 2 sine theta. Okay? So let's see. This 2 kills that 2. I have L times L, so I have L squared. So I have I L squared B sine theta, right? But what's L squared? It's the area of the silly thing. So I can just write I A B sine theta. Okay? And for reasons which you'll see later, or in a couple minutes, I can put my parentheses around the I and the A, and people give that a name. They call it a magnetic moment. That's a mu, right? The Greek mu, IA. We'll use it, don't worry. So it's mu, put a little b there if you want, b sine, whatever, theta, okay? If you had n loops, you know, one super long wire, but n loops, it would be just multiplied by n. So it'd be mu b n b sine theta. Okay? All right. Now, something you always got to be super careful of. Where does theta come in? So theta, okay, so here's the plane, right? Here's the wire plane. Okay, so here's the normal, right? The normal to the plane. Here's the B field. So the angle is the angle between the normal, right? The normal to the plane and the B field, okay? Careful, right? So in other words, if it were like this, let's say this is perfectly vertical and the B field is perfectly horizontal, then the normal would be perfectly horizontal, so the angle would be 0, right? Here, it's not 0. Here it would be 90. So just be careful of that. People always get mixed up. Where's this angle theta? So the angle is between the loop, the normal to the loop, and the field, okay? All right, so really be careful about that. Okay, so there's our equation with 1, where n equals 1, all right? All right, okay, all right. Let me talk more about this magnetic moment. So remember I said that a bar magnet is a magnetic dipole, right, with a north pole and a south pole. And then I said you could also create a magnetic dipole with a circular current loop. Remember that? Okay, so this magnetic moment, it's a vector. It points from north to south. That's all it is, not a big deal. It's equal to I times this cross-sectional area of the circle A. Not a big deal. Right? I mean, we're not going to talk a whole lot about it in Physics 106, so don't worry about it. Okay, very good. Oh yeah, don't forget too, this B, this B is an external B field, right? Remember? External B field. In other words, it's not the B field created by the current, it's an external B field. So you got to watch that too. So all these little intricacies you got to be aware of, you know. Okay, now you say, who cares? Hope you don't say that, right? Who cares? So this thing is gonna rotate, right? Well, that's an electric motor. I mean, that's an electric motor. So here, we're not going to go into gory detail, but how do you make an electric motor? You make an electric motor, you have a magnet, right? North pole, so 2 magnets, I guess, right? Or you could do it with 1 magnet. But anyway, here's the north pole of a magnet, here's the south pole of a magnet. So you have a magnetic field in the direction shown. Here you have a rectangular wire loop. You put a current in it, And guess what it does to the loop? Causes it to spin. Well, you know, so let's say I have a rectangular wire loop. Let me just use a circular one. So just pretend this is a rectangle. All right? So I have this rectangular wire loop connected to a rod or a shaft. This thing, right, is connected. Well, this thing's going to spin, right? So this shaft is going to spin. So if you have a drill bit, you just invented a drill. If you have a fan blade, you get a fan. I mean, you get a motor, all right? Because that's what a motor is. An electric motor just causes something to rotate, causes a rod to rotate. And you can add whatever you want to on it, you know? An electric beater, right, to cook stuff or whatever, you know, whatever. So this is incredible, right? An electric motor is just an application of that. Well, not that. That, right? I like this one better. That, okay? That's all it is. You just put a rectangular wire loop in a magnetic field with the correct orientation, and the thing rotates. You attach a shaft to it, a rod, bingo, electric motor. It's incredible. Right? There it is. Okay? It's incredible. So, piece of cake, right? Electric motors. What would the world be without? What would the world be like without electric motors, right? I mean, it'd be very different. Believe it or not, this is also the basis for MRI, which we're going to talk about in a few minutes. So this is all practical. Okay, let's quit.